everyone. Today we're going to learn about the mathematical constant e and its relationship to logarithms with natural log. So to do that, first we need to remember back to advanced algebra where the compound interest formula, a equals p parentheses 1 plus r over n parentheses to the nt power, was our formula where p is the starting investment, r is the rate, n is how many times it compounds per year, and t is how many years. Now, let's suppose we're putting $1 in, and I want to see how much $1 becomes after the end of the year, if it compounds monthly, daily, or hourly, or every minute. And we're going to start seeing a pattern. So, if I put it in and put $1 in and it compounds 12 times per year, and is 12, I wind up with $2.61 and a little extra, so 2.61304. If it compounds daily, 365 times a year, 2.71457. If it compounds hourly, there's 8,760 hours in a year. My dollar turns into 2.71813. Every minute, it turns into 2.71828 after a year. So as n is increasing, the result is approaching this constant called e, which is the exponential constant. Okay, this has to do with something called limits and series, which we'll get to at the end of the year. And that's why our continuously compounding interest equation is a equals p e to the rt, where e is this constant that's approximately 2.718. So because 1 plus 1 over n approaches e, as n gets infinitely large, we have this equation. So if something's compounding continuously, we're going to use the constant e. Now this relates to logarithms because logarithms are inverses to exponentials. So if we see an exponential with the exponential constant e, we have to use something called the natural logarithm, which has base e. So natural logarithm is written ln of x instead of log of x. And the base is always e. So the natural log base e of x equals y. We can convert it to an exponential, e to the y equals x. X is the argument, y is the exponent. And keep in mind that natural log always has the base e, so there's an imaginary little e written down as the base, even though it doesn't show up when we write it or on our calculator. The base will always be e if it's a natural log. So we can convert natural logs to exponentials and exponentials to natural logs using the same methods we've learned, where it's the base to the exponent equals the argument. So e, the base e to the first power equals the argument e. So the natural log of e is 1. And then if I want to convert an exponential to a logarithm, I have my base and my argument and my power. So natural log base e of x equals 7, or we just say natural log of x because we already know the base is e. So if I give you natural log problems, we should know a few of them by thinking how they look as exponentials. So the first one we have to look at is e to the 0. Anything to the 0 power is 1. E is a number. It's just irrational. It's 2.718. Now we have the natural log of 1. Just like the log of 1, it should be 0 because we have e to a certain power gets us 1. E to the 0 power gets us 1, so this answer is 0. The next problem, e to a certain power gets us e. So e to the first power gets us e. So natural log of e is 1. These two functions are inverse, and they undo each other. Now, the next problem, e to what power gets us e to the 7th? E to the 7th power gets us e to the 7th. And then we have to remember, if we're doing logs, what the base is here. The base should be 10, so 10 to the first power equals 10. So I want us to be comfortable evaluating certain logarithms and natural logs without having to use our calculator to see what they're going to show up as. And that's how natural logarithms and the constant e match up with regular logarithms, which have base 10 or any other base.